Hello, welcome to this lesson in the Linear Algebra Tutor. We're going to talk about linear independence and basis. Finally, with the title of a course called Linear Algebra, we're going to talk about something called linear independence. So as you see, we've covered a tremendous amount of material in this entire sequence of lessons. And I know that all of you know that one of the prime fundamental topics you learn in linear algebra is the concept of eigenvectors and eigenvalues. So we're moving in that direction, but we need to cover linear independence and basis so that you will fully understand what an eigenvector is and why it's important. All right, so first let me just remind you that in Volume 1 we solved homogeneous systems of equations a lot. You know, we just talked about it briefly just a minute ago actually. And that is when you have a system of equations where the right-hand side on the equal sign is all equal to zero. It's a very common situation, believe it or not, that you can pop up in nature. And we said that, just in the last section, we said that the trivial solution is when all of the variables, all the unknowns are just zero. That always satisfies AX is equal to zero. We want to know what are the cases when the solution is non-zero, when you have a non-trivial set of solutions. We gave you a test for that in the last section, so if you haven't watched that, go back and watch that right now. So let me remind you that we solved several systems of equations in Volume 1 of Linear Algebra, homogeneous systems, and one of the solutions that we got, a solution to AX is equal to 0 for a specific matrix, for a specific problem that we had a long time ago in Volume 1 was the following. So what I'm writing down now is a solution to a problem that we actually worked before. And it looks something like this. K1 times the column vector, negative 1, 1, 0, 0, plus K2 times the column vector, 1, 0, 0, 1. And I showed you how to do this. I showed you how to basically manipulate the matrix, do the row reduction, and basically you're going to end up with an infinite set of solutions like this when you have at least one row, one or two rows that are all zeros. And I showed you how to write that down and how to factor it out and how to get it into this form. What this means is that obviously x can be 0 here. That's a trivial solution. The non-trivial part of the solution is the following. I can choose any two numbers for k1 and k2. For instance, if I choose k1 is equal to 1 and k2 is equal to 1, then this vector plus this vector, the linear combination, that will be a valid solution for x. So if this were 1 and 1, then it would be this vector plus this vector. I would just add the positions up in the locations. That would be an answer, and that would be one potential non-trivial solution for that equation. But of course k can be anything. K1 can be any number and k2 can be any number. So what this means is that the solution is really a linear combination. There's that word linear again. Linear means that we're multiplying out here by numbers and not exponentials or logarithms or something. And combination means we're adding them together. So the solution really is an infinite set of column vectors x. If I lock down any value of k1 and k2, like k1 could be 10 and k2 could be negative 3, then what's going to happen is I do the multiplication, then I do the addition, I'm going to get an answer for x. And so you can see quite evidently that there's an infinite set of solutions to this homogeneous equation. All right, now we can write this. This is what we studied before. Now we're moving into new material. We can write as the following. It's not really too different, but we can say u1, we can just set that equal to negative 1, 1, 0, 0. And then we can call something u2, 1, 0, 0, 1. And when we write it like that, then the solution to the system is x is equal to k1 times u1, this is a vector, plus k2 times u2, where this is a vector. So the k's are the constants, and the u's are the vectors. All right. Now I have a bunch of words in my notes here, but I don't think it's really useful to write all these words down because it's just a bunch of writing. So I'll just cut to the chase and tell you. What is happening here is when we solve a system of equations that are homogeneous like this and we get an infinite solution set, an infinite combination of these two vectors, or these two base vectors, think of it that way. u1 and u2 must be linearly independent of one another. So I'll just write that part down. u1 and u2 are linearly independent. In this context, it basically means something very, very simple. u1 and u2 are not multiples of one another. think about it for a second. What we've said is that the answer to the problem is an infinite solution set, an infinite combination of these two, call them base vectors, right? Well, it wouldn't make any sense if u1 and u2 were just multiple. If this vector were simply a multiple of this vector, then it wouldn't even make sense to write the answer like that, because they wouldn't be two independent vectors. So writing a linear combination of two vectors that are really not independent of one another doesn't make sense. Remember, when I say one vector is a multiple of the other, think about it in terms of vectors. You know, a vector is a direction and an arrow, right? So it points this direction with this much, okay? The vector pointed this way is an independent vector of this one because it's pointed in a totally different direction. But if I have this vector and then this vector pointed in the same way, these two vectors are related to one another. They really contain the same information as far as the direction that they point. It's just that this one is larger than this one, so this one's multiple. This longer vector is simply the shorter one multiplied by a scalar. So it might maybe multiply by 2 or something. It points in the same direction, but it's just longer. Right? Those are not independent vectors because the direction is still there. The proportionality of all of the components of these vectors are all the same. So it's not really, they're not really different. They look a little different because one's a little bit longer, but as far as being independent of one another, these two are not really independent because they're simply a multiple of one another, whereas this vector is different than this one, and this vector is different than this one. Okay? Now it's a little harder to see with a vector with 4 components like this, but the concept is the same. u1 and u2 are not multiples of one another, and you can see that. There is no way that you can take vector 1 and multiply it by something and get vector 2. For instance, you have a 1 here and a 0 here. There's nothing you can multiply vector 1 by that's going to do that except for 0. And if you multiply the whole vector by 0, then the answer would give you 0, and so you wouldn't have u2. There's nothing you can multiply this set of numbers by, a single number multiplied by every location, to give you this. It's not possible. So these two vectors we say are linearly independent of one another. And when we solve solutions, homogeneous set of equations like this is all going to tie into eigenvectors later. The answers, by definition, when you get those answers down, they're all going to be linearly independent of one another. And I'll give you a hint. Eigenvectors, when we figure out what they are and we find them, they're going to be linearly independent vectors too. And if you get something that's not linearly independent, then you've screwed something up along the way. All right, so let me make sure I have covered everything. These vectors are linearly independent. They're not multiples of one another. We can see that these vectors are not multiples of one another. And by the way, I've been calling these vectors here base vectors. I've been doing that on purpose because in your book you'll see something called basis, right? These vectors are called the basis vectors, right? That's why I've done that. So you can point to u1 or whatever you want to do. These are called the basis vectors. Because when you write a solution down like that, the solution is a linear combination of these vectors. And these two vectors are kind of the fundamental ones, right? You can choose any number you want for k1 and k2. The linear combination of those vectors are going to give you the answers that the entire infinite solution set that we have. But those fundamental kernels of vectors, those fundamental ones that are there, the base vectors, that's why we call them the basis. So when you see something like, hey, write the basis down, it's just telling you, hey, find these fundamental vectors here. The whole solution is a linear combination of infinite variety of combinations of these two vectors, but the basis vectors are the ones that we find here in these column vectors from this example that we've done before. All right, so now I've tried to describe to you the concept of linear independent vectors or linear independence without really writing down the formal definition. The basic idea is you want to have vectors that are not multiples of one another. That means they're not overlapping like in the same direction. They're actually pointed in different directions. That means that they're basically going to be linearly independent of one another. But in your book, when you get to studying linear independence, you're not going to see anything like this. This is what I think is much more easy to understand. What you're going to see is a definition that looks like this: linear independence. So now that you understand what the concept is, it's much easier to understand what the book is trying to tell you. So I'll say it this way: linear independence. Vectors are linearly independent, so that's Li, if the following is true. And I will change to purple, and I will write down here that C1 times U1, this is a constant just like K1, plus C2 times U2 plus ... plus CK times UK is equal to 0 only if C1, C2, C3, ... CK are all 0. All right, that's Honestly, when I first read the definition for linear independence, I didn't understand it. It didn't make any sense. I kept reading it over and over. I knew the concept of what independence should mean, but I didn't understand after reading that what it actually is trying to tell me. This is what this definition in your book, which is almost how every definition in every book is trying to tell you. This is what it basically means. You have multiple vectors. Here's a vector, here's a vector, here's a vector, okay? So let's just say U1 is the one you're interested in. Remember we talked about here, we said U1 and U2, they're linearly independent of one another. These are not multiples of one another. Well, if you have several vectors, maybe more than two, the way that you write that formally is you say, vector 1 cannot be written as a linear combination of vector 2 and vector 3 and vector 4, however many you have. Let's just pretend for this discussion we have three vectors. We're trying to see if they're independent. Vector 1 should not be able to be written as a combination of vector 2 and 3. Vector 2 should not be able to be written as a combination of vector 1 and 3. Vector 3 should not be able to be written as a combination of vector 1 and 2. So no matter what vector you pick in your set of vectors, it should not be able to be written as a linear combination of any of the other vectors. Only then is it all three vectors, or however many you have, considered to be linearly independent. This equation formalizes what I've just told you in words, which is, I think, is easy to understand. I think you probably get that. But when you see this, you don't quite know. Well, if you think about it, U1 is here, and everything's set equal to 0. So if you were to solve this equation and pull everything on the right-hand side, then U1 could be written as a linear combination of all of these other vectors over here. U2 could be written, if you move it over there, as a linear combination of all the other vectors that you have. U3 could be written, if you move everything over, as a linear combination of all the other vectors. What it's saying is that these are linearly independent only if these constants are all 0, and that's the only way that this can be written. That's another way of saying the only way that this equation can be true, the only way that you can satisfy it, is if all of the constants out in front are 0, which means it's a trivial solution, which means that you actually can't write the vectors as a combination of the other two. You know, if I were to write U1 as a combination of U2, U3, and U4, it might be something like, well, let's just write it. It might be something like U1 is equal to 3U2 plus 2U3 or something. U1, we say, is a linear combination of these vectors. These are not linearly independent if I can do this. You're not supposed to be able to write vectors as a combination of other vectors, right? In the simple case, we say it's not a multiple. In the case with 3 or more vectors, you say that any vector you pick cannot be written as a linear combination. This is a linearly dependent set because I can do this. But what the definition is telling you, that the only way this equation can be valid is if all of the constants in front are 0. So that means this whole term is 0, this is 0, this is 0. Everything is 0. It's the only way you can get this thing to work. So let me write the second half, and we'll do it in black. Otherwise, U1, U2, U3, UK are linearly dependent, and that means, for instance, U1 can be written as a combination of U2, U3, and however many other vectors you have. This is the definition of linear independence. Let me recap again, because honestly, the first time I read it, I was totally confused about the situation. In the case of 2 vectors, it's very easy to see. Okay? We say that these are linearly independent because, for instance, this vector cannot be written in terms of this one. Even if you multiply it by something, it just doesn't work. Okay? In the case of 3 or more vectors, the way you formalize that is you say any vector you have in your set cannot be written as a combination of all of the other vectors. Right? So if you move everything over to the one side of the equal sign, you end up with this kind of equation. Something times vector 1 plus something times vector 2 plus something times vector 3 equals 0. If the only way that this can happen is if the constants are 0, which means it's trivial, okay, because the constants being 0 can always happen. If the only way this can happen is when these constants are 0, then this means that the set of vector really was linearly independent of one another. However, if you can find some values of c so that when you put them here, here, and here, and in front of your vectors, you satisfy this, then by definition you have shown something like this to be true, which means the vectors are dependent. At least one of them is dependent on the other ones. Okay? So if you can ever find a situation where at least one of the vectors can be written as a combination of the other vectors, the game is over. They're not independent vectors. We call them linearly dependent. It says right here, otherwise these vectors are linearly dependent. U1 can be written as a combination of the other vectors. U2 might be able to be written as a combination of the other vectors, and so on. All right? So I've talked about it enough. I hope you understand it. It's a little bit confusing when you first read it because this doesn't make a lot of sense, but basically when you first read it, what it's trying to say is these constants, the only way you can get this to be true, if the only way you can have that happen is when these are 0, then by definition there's no way that this can happen. There's no way that you can write one as a combination of the others. Okay, so as a test for linear independence. Obviously, this is the definition. What's the practical test? Well, what we're saying is C1 times U1 plus C2 times U2 plus C3 times U3 plus ... plus CK UK is equal to 0. This is the sort of the formalized test. We're looking for what are the values of C that can make this happen. If they're all 0, then these guys are linearly independent. If I can find a solution of C's that are non-zero, then we have a dependent set over here. So what you do is you take this and you write it as a matrix. Then, here's the important part. If the determinant of your matrix that you end up with is not 0, then you have linearly independent vectors. And let me walk you through that for a second. This is the test for linear independence. You can always have the case when all of the C's are 0 to satisfy that. What we want to know is there a non-trivial case? We've already said that if you can find any value of C's so that they're not all 0, we have a linear dependent set. And we also learned in the last section that if you have a homogeneous set of equations, notice this is all equal to 0, and this is basically a bunch of equations because all the U's here are representing multiple variables. This is a matrix equation. What we have here, let me walk you through this. This is the test, the determinant test to figure out if we have linear independent vectors or not. What we have here is a homogeneous set of equations. Homogeneous because a 0 is here, and this is a matrix equation because every U here represents multiple variables because they're vectors, right? And then the C's out in front are what we're trying to solve for, okay? So basically we learned before when we're talking about determinant test for homogeneous systems is that when the determinant was not equal to 0, this means that only C is equal to 0 is a solution. In other words, the trivial solution. The trivial solution is the only solution, which is basically what the test for linear independence is asking us. It's saying, hey, this is the test, and it's linearly independent vectors only when these values of C is 0. That's the trivial case. What's the test to see if we have trivial solutions only in our solution space? We take the determinant. If we get an answer that's not equal to 0, then that means the trivial solution is the only solution we have. And that means that these vectors are going to be linearly independent. So make sure you understand that. I'd like to solidify this with a couple of quick problems. I think it's going to become very easy once you see that. For instance, what if we have a couple vectors? U1 is 1, 0, 0, like this. U2 is 0, 1, 0. U3, 1, 1, 0. So those are my 3 vectors. I want to figure out, are these vectors linearly independent of one another or not? And that means fundamentally, do they point in different directions, or can you write them as multiples of the other vectors? In other words, can U1 be written as a combination of any kind of U2 and U3? Can U2 be written as a combination of any of the other 2 vectors? Can U3 be written as a combination of any of the other vectors? And so the test for independence, as you know, I'm going to write it down one more time. The test is C1U1 plus C2U2 plus C3U3 is equal to 0, but this looks deceptively simple because this is really a matrix equation. U1, U2, and U3, you can see they each contain 3 elements. So really, if you were going to write this down as a matrix equation, you would write the following. You would have a coefficient matrix, and you would take your vectors and you would write them vertically down. I will show you why you do that in a minute. U1 is 1, 0, 0. U2 is 0, 1, 0, and U3 is 1, 1, 0. Okay, so this is the coefficient matrix. Let me just not label it like that. That's going to get cumbersome here. We have the matrix here for the vectors, the u's, and then we're going to be multiplying it by a column vector, C1, C2, C3, and we're asking ourselves, when is that equal to 0? What values of C make this equal to 0? Make sure you understand this. What we've done is we've taken our 3 test vectors and we've arranged them vertically. The reason we arrange them vertically is because when you multiply across and down, you have 1 times C1, 0 times C2, 1 times C3. Notice that we have the components of U1 is the only thing multiplied by C1. If we go across and down, this one gets multiplied by C1. If we go across and down, this guy gets multiplied by C1. If we go across and down here, the first element again is multiplied by C1. So because we're trying to fit it into the form of this equation, the elements of U1 are the only thing that gets multiplied by C1. So to do that, we write the elements of U1 down. It's something I'm explaining to you, but really what you just need to get in the habit of doing is when you're testing for linear independence, you write the test vectors down in a matrix, and then you have the C matrix and so on. So these vectors are linear independent if the determinant is not equal to 0. So let's go ahead and see if that's the case. The determinant of this matrix 1, 0, 1, 0, 1, 1, 0, 0, 0. What is the determinant of this matrix? Well, we learned a trick from before. We have a row that has all zeros. So we know that because of that, the determinant of this actually is 0. We've talked about the fact that when we do a cofactor expansion about this row, it's going to give us a determinant 0. So because this test for linear independence is like this, this tells us that this is a dependent set. Or these are not linearly independent, which means that these vectors, as different as they look, are not truly independent of one another. At least one of them can be written as a combination of the others. Let's see if we can figure out what the trick is here. So if we go up there, in fact, if you look, U3 is actually U1 plus U2. Think about it. This is equal to 0 plus 1. This 1 is equal to 1 plus 0. This 0 is equal to 0 plus 0. Because U3 can be written as a combination of the other 2 vectors, these are not independent vectors. These are not linearly independent vectors, and the way we tested that is we put our vectors in a column form, we took the determinant, we found out that it was actually identically equal to 0, and that means it's a dependent set. If we have gotten any other determinant other than 0, we would have an independent set of vectors. So I'd like to turn your attention to the last problem where we'll test it. And this set, I will give you a hint, is going to be linearly independent. So let's say U1 is 1, 1, negative 1, U2, 0, 1, 1, U3, 1, 2, 3. So the bottom line is the test for linear independence in matrix form, you write it as a column. 1, 1, negative 1. Write it as a column. 0, 1, 1. Write it as a column. 1, 2, 3. This is multiplied by C1, C2, C3, and we're seeing when is this equal to 0. Now you know that you've written it right because if you go across and down, across and down, across and down, the only thing multiplied by C1 is U1. The only thing multiplied by C2 is U2, and so on. So when you write it this way, you're guaranteed to set it up correctly. So what is the determinant of this matrix? 1, 0, 1, 1, 1, 2, negative 1, 1, 3. You can do it any way you want. You can do cofactor expansion. You can do row reduction. But what you get is 3, the number 3. And since this is not equal to 0, and since the test said that if you get a determinant not equal to 0, it's a linear independent. So this is a linearly independent set. The reason the determinant test works is because when we get an answer that's non-zero, the only way that it can actually, what it points to is that the solution of this set of equations, the only one that works is when C1, C2, and C3 are all 0. So the test for linear independence is if you get a determinant of this matrix when you form the column vectors as columns, and you take that determinant and you get a non-zero answer like this, it's linearly independent. The reason why that is true is because the test for linear independence comes from a homogeneous matrix equation, and we're looking to see what type of solutions come out of that, and the bottom line is the determinant tells you what type of solutions. So notice though that in all of these problems we have a square matrix here and we have a square matrix for the other problem we did. So this test for linear independence of vectors only works when you have a square matrix, so which is most of the time. Most of the time you have three vectors with, you know, 3 components each or something, and you're trying to see if they're independent of one another. So it's going to work almost all the time. But if you are trying to test when you don't end up with a square matrix here, you might have to use some other methods to figure out if they're linearly independent. And I'm going to cover some of those in a future lesson at some point. But the most important thing for this lesson is for you to understand, what does linear independence mean? I think we've covered that extensively. And the bottom line is that when you take those test vectors you have and you arrange them vertically in a matrix, and if you end up with a square matrix and you take the determinant, if you get a number that is non-zero, then these vectors, the original ones, are linearly independent. But if you arrange these guys and you get a determinant of 0, then these are a dependent set of vectors where truly they're not totally independent of one another. At least one can be written as a combination of the other ones. So now we've covered the fundamental requirements needed to go off and talk about eigenvectors. So let's do that now. Make sure you understand the concept of linear independence, and let's go talk about eigenvectors and eigenvalues.